Okay, so in our last lecture, we were looking at planning question, right? But today we'll move back into the last bit for chemical equilibrium. Okay. Any questions, please upload on Slido. Just want to highlight that in our last lecture, what we did was we looked at how changes in the equilibrium system, like concentration change, pressure, temperature change, and catalyst. We haven't looked at catalyst yet, look at temperature. How it will change. How it will change the system, and how would the system react and respond to the change by counteracting the initial change. Okay, so we asked you to go back and look at checkpoint 6, right? Okay, so what happens as a result of this temperature change to the reaction between dinitrogen oxide and NO2? The enthalpy change is positive. So when you place the whole reaction mixture in ice water, how will the equilibrium position shift? The equilibrium position will shift to the left. Why shift to the left? Because it wants to favor the exothermic reaction. As a result of the shifting of equilibrium position to the left, okay, the equilibrium constant will decrease. Okay? Alright, because when your temperature drops, okay? Alright, when temperature drops, your Kf drops more than Kb. Okay, so your equilibrium constant Kc will decrease. So how will you observe the change? The color of the mixture will lighten to pale brown. Okay? Okay? Right, but if you put the whole reaction mixture in hot water, what is going to happen? Okay, the equilibrium position will now shift to the right to favor the endothermic reaction, to remove some of the added heat. And as you remove some of the added heat, okay, because of the higher temperature, your Kf, okay, will increase more than Kb. Rate constant of forward reaction increase more than rate constant of backward reaction. So Kc will increase. Okay? And the color of the reaction mixture will darken to dark brown. Okay? Right, so now let's move on to the last change that we can apply to a system at equilibrium, okay, which is a catalyst. So let us just consider the energy profile diagram of a reaction without catalyst. This is the energy profile diagram from reactant convert to product. Okay? You have your forward reactions activation energy to give the transition state, and then it will go to the product. For the backward reaction, the product will form reactants, right? So for backward reaction, this is the activation energy of backward reaction. So you need to go up this way to reach the transition state before reacting to form the reactants. Okay? When you add in a catalyst, the energy profile diagram changes. You find that the maximum of the energy profile drops to a lower level. Okay? The activation energy for forward reaction is now smaller. Same for the backward reaction activation energy. What you can also note is that the activation energies for both the forward and backward reactions are lowered to the same extent, which is this one. The extent of the change is here. Okay? This has some implications. Because the activation energy is lowered by the same extent, catalysts basically increase the rate of both forward and backward reaction to the same extent. So both forward reaction is faster and backward reaction is faster. Okay? Activation energies of both forward and backward reaction are lowered to the same extent, which means that the rate constant for forward and backward reaction, Kf and Kb, will increase by the same extent. Okay? Therefore, catalysts, this is important, will not affect the equilibrium position because they speed up the forward and backward reaction to the same extent. So there is no net shifting of equilibrium position. So equilibrium position doesn't change. Likewise, equilibrium constant doesn't change as well, because the increase in Kf and Kb is to the same extent, so they will cancel out. Okay, so Kc will still remain the same. Okay, so what do catalysts do? Catalysts merely increase the rate at which you reach equilibrium. So it only speeds up the reaction rate to reach equilibrium, or shorten the amount of time required to reach equilibrium. But the percentage of product remains the same. The yield remains the same. So using catalyst does not increase the yield of the product. Of course, nor of the reactant. Okay? So when I add in a catalyst, it only changes the rate at which equilibrium is established. No shifting in equilibrium position. Okay? Alright, no change in equilibrium constant. The only change is the increase in the rate to reach equilibrium. Okay? Alright, so if you look at the table that you have on page 23, that's basically a summary of what we have learned last Wednesday and just now. If you consider a reversible reaction, A plus 2B equals 3C plus 4D, enthalpy change is less than 0 when concentration of A, N or B increases. Either one of it increases or both increases. Forward reaction rate will increase. The rate of forward reaction will be greater than rate of backward reaction. Okay? And so at this point in time, I must pause and look at this in greater detail, and I must explain myself. Okay? Because if I don't explain myself for this, the question that you will ask me is, but Mr. Tan, didn't you tell me that in the system at equilibrium, the rate of forward reaction is equal to the rate of backward reaction? Right, we said that, right? So why is this still shown? Okay, I must clarify. What I meant by this bit over here is that as a result of an increase in concentration of A or B or both, okay, the system's equilibrium has been disturbed. And this is the response of the system to try to counteract the change. So this is not permanent. The rate of forward reaction will be faster than the rate of backward reaction until you reach the new dynamic equilibrium. And when you reach the new dynamic equilibrium, rate of forward reaction will be equal to rate of backward reaction. So then it still will be at equilibrium. But now it's not at equilibrium because I have just disturbed equilibrium. So this will kick in, okay, until you reach the new dynamic equilibrium. So for the equilibrium position, it will now shift to the right to favor the formation of more product, but the equilibrium constant remains unchanged. Okay? Likewise, when you decrease the concentration of A, N or B, the forward reaction will now decrease. And the rate of backward reaction will be higher than the rate of forward reaction, once again, until you reach the new equilibrium. Okay, because now I just disturbed the system at equilibrium. Equilibrium position will now shift to the left, but your equilibrium constant remains unchanged. Okay? When I increase the concentration of the product, C, N, or D, the backward reaction will increase. Rate of backward reaction will be larger than the rate of forward reaction until you reach a new equilibrium. Equilibrium position will now shift to the left, no change once again to equilibrium constant. Okay? Which is consistent with what we were talking about last Wednesday. Okay? So now if I were to change pressure, so if I were to increase pressure, so let us assume that A, B, C, D are all gases. Okay? If not all of them are gases, and there is a change in pressure, you only need to consider the gaseous component. Okay? So in this case, if you look at the stoichiometric coefficient, there's 1 mole of A, 2 moles of B, 3 moles of C, 4 moles of D. The number of moles of gaseous product is higher than the number of moles of gaseous reactants. So when you increase the pressure, the overall rate will increase because the concentration of all of your reactants and products go up, right? So forward reaction, backward reaction will all increase. But the rate of backward reaction must be higher than the rate of forward reaction. Agree? Because for the backward reaction, it is raised to a higher power, right or not? Okay? So for the same change in partial pressure, the backward reaction will now proceed faster. Which is consistent with the Chatelier's principle. Because the Chatelier's principle says, when you increase pressure, the system will try to counteract the increase in pressure by favoring the formation of species with a lower volume. And that means you will favor the reaction that produces a lower number of gaseous molecules, which is to favor more reactant formation. Because reactant, only 3 moles of gas, product, 7 moles of gas. So it's going to favor the backward reaction more. So that's consistent, right? So the equilibrium position will shift to the left. And the equilibrium constant remains unchanged. Okay? When you decrease pressure, it's the opposite. Based on this stoichiometric coefficient. Overall rate decreases because the partial pressure and hence concentration of all reactants and products drop. Rate of forward reaction must be higher than rate of backward reaction because according to LCP, the system will now try to favor the reaction that produces a higher number of moles of gaseous particles, which is a forward reaction. So this equilibrium position will now shift to the right, and the equilibrium position will remain unchanged. Okay, so this is what we have been learning last Wednesday. Okay, what happens when you increase temperature or decrease temperature? When there is a change in temperature, what you need to focus on is no longer the stoichiometric coefficient, but you need to focus on the enthalpy change. The enthalpy change is negative, which means it is exothermic. So when I increase temperature, overall rate must increase for both forward and backward reaction. So overall rate must increase. But which one increase more? Okay, the rate of the backward reaction will increase more than the rate of forward reaction. Why? Because according to LCP, the backward reaction will be endothermic, right? So based on LCP, when temperature goes up, the endothermic process will be favored to try to absorb some of the added heat. So the backward endothermic reaction will be favored. So what is going to happen is that the increase in Kb backward reaction will be higher than the increase in Kf. Okay, the equilibrium position will shift to the left, and the equilibrium constant will decrease. This is when you see a change in the equilibrium constant. Okay? Right, so at this juncture, I must stop. and I will ask somebody in the lecture group, under what circumstances, when I increase or decrease temperature, Kc will not change? Let's see. 5K is here, right? 5K. Sean Lim. Where's Sean? Where's Sean? Okay, Sean. Under what conditions will temperature change, but there will not be a change in equilibrium constant? Only in one special case. So under what special conditions will a change in temperature not give rise to a change in equilibrium constant? Very special. When the enthalpy change is zero. Okay, when enthalpy change is zero, you will not be able to favor forward or backward reaction, so there's no change in terms of the Kc value. Okay? Alright, so when you decrease temperature, it's the opposite. So rate of forward reaction increase more than the rate of backward reaction. The decrease in Km is more than the decrease in Kb. So that's why the equilibrium position will shift to the right and your equilibrium constant will increase. Okay? And this is what we have learned. When you add in the catalyst, the overall rate must increase for both forward and backwards. But no change to equilibrium position. And likewise, no change to the equilibrium constant. Okay? Alright? So what have we learned so far based on last Wednesday's lecture? We have learned about Le Chatelier's principle and how the changes in conditions like concentration, pressure, temperature, how it will affect the rate of forward and backward reaction, how it's going to affect the equilibrium position, and how it's going to affect the equilibrium constant. Now, the next part of the lecture, we will then look at how delta G naught affects K, and likewise how K, equilibrium constant, affects delta G naught. We will also look at the Haber process. Okay? Now, if I do a quick recap of what we have learned previously, over here, we have also looked at how your equilibrium constant K is related to kinetics, right? Because the rate of forward rate constant of forward reaction over rate constant of backward reaction is going to give you your K value, equilibrium constant. Okay, so now we're going to link, so we have already linked equilibrium with kinetics. Now we're going to link equilibrium with energetics part 2. Okay? Alright, so before we do that, I'm going to just introduce this bit to you. I want you to consider a reversible reaction. A plus B forms C and D. I have some statements that I want to go through. If you think about it, it makes sense. Any shift in equilibrium position, okay, to establish dynamic equilibrium must be a spontaneous process, right? Which means that when I shift an equilibrium position, there must be a change in delta G. And the change in delta G must be negative. Which means that there is a reduction in the Gibbs energy. Okay? When I reach dynamic equilibrium, I no longer favor forward nor backwards reaction. So your Gibbs energy, G, must be at a minimum level, such that there is no incentive for the reaction to proceed. Okay? Either forward or backwards, because it's going to lead to an increase in the Gibbs energy, which it doesn't go, which is not spontaneous. So delta G at dynamic equilibrium, the change in G must be equal to 0. Okay? So with these two statements, we will now look at how delta G changes. Okay? Consider a graph that looks like this. Huh? I'm going to explain to you what it means. The x-axis, left-hand side here, is pure reactant, which means it's 100% reactant. At the right-hand side of the axis, and this is pure product, which is 100% product. So when a reaction proceeds from reactant to product, it basically moves from here all the way to right-hand side. Okay? But because it's a reversible reaction, it doesn't go from pure reactant to pure product. Okay? Alright? The y-axis, there are two, because we don't know how you're going to compare the Gibbs energy. If you are looking at it from pure product, it's easier to use the axis on the right, y-axis on the right. If you are looking at reactant, it's probably easier to look at the y-axis on the left. But these two y-axes are the same thing. They both represent Gibbs energy, G value. Okay, so this represents high G value, this low G value. Okay? So as I move here from 100% reactant to 100% product, somewhere in the middle is 50% reactant, 50% product. Right? And, okay, so what happens here? At the minimum of your G, it must be the position of equilibrium. Right? Okay? At the dynamic equilibrium, G must be at the minimum value of Gibbs energy. So the delta G is equal to 0, and Q, which is your reaction quotient, must be equal to equilibrium constant. Okay? And, so now if I look at a forward reaction, when I proceed from 100% reactant and I start the forward reaction, what is going to happen? Think of it as a person cycling, a person on the bicycle at this point in time. This person on the bicycle, without even pedaling, will automatically roll down the slope, right? Correct? Will roll down the slope. Okay? They will, which means that the reactant will also roll down the free energy slope. Okay? Because if you look at the G values as I move from the reactants to product, the change in G is negative, which means it is a spontaneous process. Okay? So from here to here, it is a spontaneous process. Right? So reactant will move towards equilibrium or dynamic equilibrium. So reactants will form product. The forward reaction is spontaneous from this point to this point because the change in G is negative. Okay? If you go and calculate Q, your reaction quotient, it will be lower than Kc. Okay? Now, but past the equilibrium point, if I still want to continue with the forward reaction, it's going to be very difficult, right? Because now, the bicycle will tend to remain in the valley here at the minimum and will not move up towards 100% product. Okay? So for the forward reaction from equilibrium to 100% product, it is not spontaneous anymore, right? Because the change in G is positive. Okay? But if you started off with 100% product, it will be a spontaneous reaction to go from 100% product to equilibrium, right? Because the backward reaction is now spontaneous and your delta G is negative. Okay? Alright? So if I look at the backward reaction from 100% product to equilibrium, this process, the delta G is negative. If I calculate Q, reaction quotient, it will be larger than Kc. So that's why the backward reaction will be favored. Okay? Alright, so what can we say? We say that for a spontaneous reaction to occur, it must be accompanied by a reduction in the Gibbs energy. So G must decrease, which means your delta G must be negative. So if I start off with 100% reactant, it will naturally go down to form equilibrium here. Okay? Okay? So I show again. You look at how the red dot moves. It will favor formation of more reactant, more product, until a point in time. It will go for more product. Okay? And if you have started with pure product, it will also go down to the equilibrium over here. So a reaction mixture which is reversible will tend to adjust its composition until G is at minimum. And at this point in time, okay, you will have dynamic equilibrium. So at composition A here, at this composition, slope of G is negative, the change in G will be less than 0. So the forward reaction will be spontaneous. A and B will tend to form more, C and D. Okay? The rate of forward reaction will be larger than rate of backward reaction. Equilibrium position will lie to the right. Okay? It will favor forward reaction. Okay? Q will be less than Kc. Okay? Now consider composition B. Slope of G is positive. Okay? Alright? The delta G for forward reaction is positive. So forward reaction is not spontaneous. But backward reaction is now spontaneous. Okay, so C and D, the product, will form more A and B. Okay? So the rate of backward reaction will be more likely to take place than forward reaction. Okay? And your reaction quotient Q will be larger than Kc. Okay? When you have reached the minimum here, slope of G is 0, which means the change in G is 0. At this point, G is at minimum, the Gibbs energy. You have reached dynamic equilibrium. There will be no further change in composition, as the reaction will not be spontaneous in either direction. Okay? And at this point in time, the rate of forward reaction will be equal to the rate of backward reaction. Okay? Alright? So therefore, at the minimum, there's no change or no shift in equilibrium position. Okay? Now I just want to introduce an equation to you. How do we relate delta G naught? Delta G is equal to delta G naught plus RT ln Q. R is your gas constant. T is the temperature in Kelvin. Q is the reaction quotient. Okay? Alright? Consider a system at equilibrium. If a system is at equilibrium, delta G is equal to 0, right? Which means Q is equals to K, Kc. So if I substitute these values in, 0 is equals to delta G naught plus RT ln K. Which means that delta G naught is equals to minus RT ln K. Okay? Now this equation, okay, will help us link delta G naught with K. And this is what you need to know, how to relate delta G naught with K. Okay? Which means if I give you K, you can determine, sorry, if I give you delta G naught, you can determine K. Likewise, if I give you K, you can determine delta G naught using this equation. Okay? Alright, and how to find delta G naught? You can find it using the Gibbs free energy change equation. Okay? So what is the use of this equation? Delta G naught equals to minus RT ln K. Okay? Delta G naught is a constant for a given reaction at a constant temperature. The sign of delta G naught tells us whether the reactants or products are dominant at equilibrium for that reaction. This is what your syllabus document tells you that you must know. What does the sign of delta G tell you about K? And how much reactant, how much product exists at equilibrium? Okay? So we'll try to use the equation to help us, this equation. Okay? Right? So case 1. I want you to consider a reaction where delta G0 is negative. If delta G0 is negative, okay, there is a negative sign here, R is 8.31, T is positive because it's measured in Kelvin, which means that this is positive, this is positive. It means that ln K must be positive also, right? When will ln K be positive?